Hello student, this is our second chapter. We're now going to talk about molecular structure. We're starting today with writing Lewis structures, talking about formal charges and resonance structures. So remember, chemical properties of elements are determined by their valence electrons. For that, use the periodic table, but ignore filled d and f orbitals. As we have said before, noble gases are very stable as they have full electronic configuration. They are not reactive at all. We use the Lewis convention in which the chemical symbol stands for the nucleus and inner electrons. Then we show the outermost or valence electrons by dots. Sometimes we will use a line that represents a pair of electrons. Lewis diagrams are best when we only have s and p electrons. They're not great when we have d electrons. You can use a periodic table, but it will be very helpful to you if you know the first octet period shown here, especially that carbon has 4 electrons, nitrogen has 5 valence electrons, oxygen has 6 valence electrons, fluorine has 7 valence electrons. We know the Lewis diagram for all atoms in the periodic table. Remember that an element that is below another one in the same column has the same valence electrons. So sulfur is below oxygen. It has the same number of valence electrons than oxygen, 6. To write a Lewis diagram, we need to know the electronic configuration of the atom or its position in the periodic table. Atoms will want to achieve a complete outer shell, which is the octet status. And they'll do that either by losing or gaining electrons. We've seen that before. So sodium would lose an electron to become sodium plus, or chlorine would gain an electron to become the chloride ion. Otherwise, they will be sharing electrons in covalent bonds. This brings us to covalent Lewis diagrams of molecules that we are going to study next. Okay, single rules to draw Lewis structures. First, we're going to determine the number of valence electrons, V, using all of the elements making up the molecules. So this is when it's interesting to know that nitrogen has 5, oxygen has 6, carbon has 4, etc. We are careful not to count d electrons if the d orbitals are full. If you don't remember these guys, you will have a periodic table. Then we draw a skeleton structure using single bonds. Each bond takes 2 electrons. We count the electrons in those bonds and we subtract the electrons that we've just used from the total number of valence electrons. Then we distribute the remaining electrons so each atom achieves an octet status, starting with the most electronegative elements. If we don't have enough electrons to satisfy an octet rule on all atoms, we use double or triple bonds to share electrons between these elements. If we have too many electrons, then we add extra electrons as lone pairs to the central atom, being careful that the elements in the second period have to follow the octet rule. Elements in the third period and beyond can have more than 8 electrons do not have to follow the octet rule because we have accessible to us the empty d orbitals. Okay, let's try with NF3. So N, nitrogen, has 5 electrons, fluorine has 7 electrons, so our valence electrons are 5 plus 3 times 7, 26 electrons. Then we draw our skeleton with the nitrogen and the 3 fluorine. Each bond takes up 2 electrons, so that's 6 electrons. We have left 26 minus 6, 20 electrons to place. The most electronegative elements are the fluorine, so we put 6 electrons around each of the fluorine, and then we have 1 lone pair that we can put on the nitrogen. We have placed all of our electrons, so we are good. The octet rule is followed. Nitrogen here has 2, 4, 6, 8 electrons. Let's try another molecule, C2H4. So carbon has 4 electrons, hydrogen has 1 electron. So the number of valence electrons is 2 times 4 plus 4 times 1, it's 12 electrons. We draw a molecule, a skeleton, where we connect the 2 carbon because we know that hydrogen can only have 1 bond. So we draw this molecule with the 2 carbons connected to one another and the 4 hydrogens around. Then we have 2, 4, 6, 8, 10 electrons. So we have 2 electrons left to place. In order to meet the octet rule for both carbons, we place the electrons in a covalent bond between the 2 carbons. So each carbon now meets the octet rule, 2, 4, 6, 8 electrons. So we're good. Okay, let's do N2O with the skeleton NNO. Nitrogen's 5 electrons, 2 times 5, oxygen 6, total number is 16 valence electron. We draw a skeleton, uses up 4 electrons. We have 12 electrons left to place, so we put 6 on each of the nitrogen and the oxygen. But let's look at the octet now. If we look at the octet, we see that nitrogen here has 8 electrons, 2, 4, 6, 8. Oxygen also has 8. But nitrogen here has only 4 electrons, so it doesn't have a full octet. So we need to share electrons in order to have a full octet around this nitrogen. So we do so by making double bonds between the nitrogens and the nitrogen and oxygen. So now here we have a full octet around each element. Now let's look at the formal charges. The formal charge, remember, it's the electrons that the element owns. So the nitrogen here owns the 4 electrons in the lone pairs and 1 electron per covalent bond. So 1, 2. So here it has altogether 6 electrons. Nitrogen, neutral nitrogen, has 5 electrons. Therefore, this is a -1 formal charge. It has 1 extra electron. Nitrogen in the middle has 1, 2, 3, 4 electrons. So it is short 1 electron. It's +1. Formal charge is +1. The oxygen here has 1, 2, 3, 4, and then 1 electron per covalent bond. 5, 6. It has 6 electrons. The formal charge is 0. So here we have a molecule with a -1 on the nitrogen and a neutral oxygen. If you recall what we saw in module 3, we saw that oxygen was the second most electronegative element of the periodic table, meaning it's pulling electrons towards itself. So having a neutral oxygen while we have a negative nitrogen doesn't work. it's better to have more electrons on the oxygen. So we can move electrons from the lone pair here down to the nitrogen. We cannot keep it that way because otherwise we'd have 10 electrons on this nitrogen. So we pull electrons to the oxygen to the outside. So it's a push and pull. And we end up with this Lewis structure where we have kept the octet on each atom. But now if we look at the formal charges, the nitrogen here has 1, 2, 3, 4, 5 electrons. So it is neutral, 0. Nitrogen in the middle has 1, 2, 3, 4, so it's still plus 1. And the oxygen here now has 1, 2, 3, 4, 5, 6, 7. It has 1 extra electron, so it is minus 1. You have just written your first resonance structures. These are 2 resonance structures, and we use this double-headed arrow to represent their relationship. So remember, push, pull, and you get to a new resonance structure. And this is a better resonance structure, a better Lewis structure for this molecule because the negative charge is on the most electronegative element, which is the oxygen. So let's summarize what we just practiced in deducing formal charges of the nitrogens and oxygen in N2O. To deduce formal charge of an atom in a molecule, we assign 1 electron for each shared electron pair, which means 1 electron for each covalent bond. And then we add this number to the total number of unshared lone pairs of electrons. If we end up with a number of electrons that is smaller, so if we have a fewer electron than the neutral atom has in the periodic table, the element has a positive charge. If we have more electrons than the element has as a neutron atom, then the element or the atom in that molecule has a negative charge. Pay attention. The sum of the atomic formal charges has to match the charge of the molecule. So if we're looking at a neutral molecule, the sum of these atomic formal charges has to be 0. If we are looking at an ion, the sum of the atomic formal charges has to match the charge of the ion. Okay, let's do a couple of examples. First, NH4+. So nitrogen has 5 electrons, hydrogen has 1 electron. So number of valence electrons is 5 plus 4 times 1. But do not forget that we have a positive charge, so we are missing 1 valence electron. So it's a minus 1 here. So altogether we have 8 valence electrons. We draw our skeleton. Nitrogen in the middle, the hydrogens around. We have used 2, 4, 6, 8 electrons. We've used up all of our electrons. Let's assess the formal charge on the nitrogen. Here, nitrogen owns 1 electron per covalent bond. So 1, 2, 3, 4. It has no lone pairs. So altogether, it has 4 electrons. So it's 1 short from a neutral nitrogen. So this is where the positive charge is located. Let's take another example. This molecule here. First, let's look at the structure of the methyl group. So a methyl group is a carbon with 3 hydrogens. So the carbon is bringing 4 valence electrons, the hydrogens 1 electron each, so we have altogether 7 electrons. So we draw our skeleton. A methyl group looks like that. Carbon in the middle, 3 hydrogens. That takes care of 6 electrons. We have 1 electron left. So that's a radical at this point. So we use that now to build our Lewis structure for the full molecule. So we have 3 methyl groups, so 3 times this CH3 radical, a nitrogen with 5 electrons, an oxygen with 6 electrons, so altogether we have 14 electrons. We draw our skeleton, nitrogen in the middle, 3 methyl group, and the oxygen. That takes care of 2, 4, 6, 8 electrons. We have 6 electrons left to place, so we're going to put them on the oxygen as 3 lone pairs. Now let us assess the formal charges. Starting with the nitrogen. Nitrogen here owns 1, 2, 3, 4 electrons. So it is short 1 electron. So it's a positive charge here. Oxygen, 1, 2, 3, 4, 5, 6, 7. It owns 7 electrons, which is 1 extra from neutral oxygen. So it has a negative charge. So you see that overall, our molecule is neutral as it should be, with a positive charge and a negative charge. You can also assess this molecule and for the octet around each atom, and you'll see that all of them have full octets. Earlier on, we already started to talk about resonance structures. These represent the ability for electrons to move within a molecule. It is demonstrated by the possibility to write multiple Lewis diagrams. So let us look at ozone as an example, O3. We have 18 valence electrons, so correct Lewis structures are represented in both of these diagrams. The central oxygen has a positive formal charge in both, but the negative charge is on the oxygen to the right in this molecule, while it is on the oxygen to the left in that structure. We will show that electrons can move between these 2 oxygens by using curved arrows. Remember that the central oxygen cannot have more than an octet. So if we push electrons towards the central oxygen, we have to pull electrons away from it. So with curved arrows, we push electrons towards the central oxygen and we pull electrons away from it. When we do that, we end up with 3 lone pairs on this oxygen together with a negative charge. And now this oxygen has a formal charge of 0. The electrons can move back, push and pull, and we get back to this Lewis structure. So these are 2 resonance structures for the ozone molecule. We represent that these are resonance structures of one another by using these double-headed arrows. The reality is that the electrons are constantly moving back and forth between the 2 oxygen. So the true state of bonding is never correctly represented by any one of these Lewis diagrams. The reality is somewhere between these 2 extremes. This is called a delocalized bonding, meaning that the electrons are constantly moving between the 2 oxygen. This is actually extremely stabilizing of the molecule. Altogether, we can say that the oxygen-oxygen bonds are equivalent to 3/2 bonds. In other words, we have 3 covalent bonds that are divided or split up between 2 oxygens, 3 bonds over 2 elements, so it gives them 3/2 or 3/2 or 1.5 bonds to the central oxygen. Let's look at the ion NO3-. Here's a correct Lewis diagram for this ion. Nitrogen here has a formal charge of +1. Both oxygens here have a formal charge of -1. Overall, this structure has a formal charge of -1. We can write resonance structures by moving the electrons. Push and pull, we end up with this new Lewis diagram. We can keep moving electrons. Push and pull, we end up with this new Lewis diagram. No single structure represents the ion accurately. The electrons are delocalized over the 3 oxygens. As a matter of fact, all NO bonds are equivalent to 4/3 bonds. You have 4 covalent bonds spread out over 3 atoms. Each oxygen atom has 1 1/3 bond to the nitrogen. Now let's look at the acetate ion, CH3CO2-. We can write a Lewis diagram for this ion here, but we can also write resonance structures. We can push and pull electrons, so we can write this other resonance structure for the acetate ion. Here again, neither of these Lewis structures are representing the acetate ion accurately. The reality is that the electrons are delocalized between the 2 oxygens. We can represent it like this. No single structure represents the ion. The 2 carbon-oxygen bonds are equivalent, and we have 3 covalent bonds split out over 2 elements, 2 oxygens, so they're equivalent to 3/2 bonds, or 1.5 bond. So this concludes our module number 4. Now go and take up activity number 4. Bye for now.